All right, shape function. So we have our connectivity here. We just described we have our local and our global numbering. And so what happens is we're going to look at this master element. Okay, we're going to take a look at this element here. In the local numbering scheme, the first node will be numbered 1 and the second numbered 2. Okay, so we just said that. This is that master element again. And what is important, so here we go like sort of counterclockwise, and most element numbering schemes go that way. Order does matter. You can't flip these. All the theory that we're developing now is based on this numbering that goes left is on 1 is on the left and 2 is on the right. Okay, so that's kind of one point, and we'll come back to that again as we'll talk about numbering order and as we go forward with other type of elements. Okay, so we have the x1 represents the x-coordinate of node 1, x2 represents the x-coordinate of node 2, and we define what's called a natural or intrinsic coordinate system denoted by psi, okay, the Greek letter psi. And this is a kind of neat little function. It's given right here. So if you look at the math in here, psi is equal to 2 divided by x2 minus x1 times the quantity x minus x1 minus 1. And what happens is this function takes wherever you're at, okay, x, whatever location, and your x1 over here, okay, your x2, these are actually the coordinates of your nodes. It takes those and it transforms it to basically -1 to 1 in that range. So it turns out that these master elements, as we call, we have truss now, we're going to have triangles, we're going to have quads, all this stuff. They range, most of them I've seen, range from -1 to 1. Okay, this is like what we call psi space, or natural coordinate system space, or there's an isoperimetric space. There's lots of different terms people use. But the important thing is that the master element ranges from -1 to 1. And so what we do when we come into our element routine, called the element routine in the implementation, it comes in and it says, okay, where are you at within this element? Okay, and I can convert that down to natural coordinate system space. It goes from -1 to 1. Another way to put that is if my x-coordinate, let's say, is 1 billion, or I don't know, that's a big number, 100,000, and node 2, the x-coordinate is 200,000. Even though those numbers are huge, they represent meters or centimeters or whatever, it will always scale it down to -1 to 1 when we put it into this equation. Okay, so that is the mapping, called a mapping, that we use. And now let's just punch some numbers in here to explore what that means. Okay, in this example, it says for the element shown, evaluate the intrinsic coordinates at x equals 0 and x equals 1. All right, so we have our mapping function here that we're going to use, and what we're going to do is basically plug in our values for x2 and x1. So we can write so at x equals 0, we have psi is equal to 2 x2. x2 is equal to 1. 1 minus 0 is x1. Okay, so this would be x2 and x1. And then we have x. What's our x? Our x is 0. So we're going to say 0 here, minus x1. x1 is 0 minus 1. So from this quantity is equal to 0, and so this is going to be equal to -1. Okay. All right, next question. At x equals 1. At x equals 1. Same thing. We have our psi function is equal to 2. This is always the same, x2 minus x1, so it's always the same thing. And then the quantity here, x is equal to 1 minus x1, which is 0 minus -1. and that's going to be equal to 2 over 1, 1 minus 1. So that's going to be equal to 1. Cool. And that's basically, it turns out that that is the same as our intrinsic coordinate. So notice here that the 0, though, the 0 mapped to -1. Okay. 0 maps to -1. All right, and that's our master element. So do you want to take a guess at where 0.5 would be? Where do you think that would be? Let's compute it. So we have psi is equal to 2, 1 minus 0, 0.5 minus 0, minus 1. That's going to be equal to 2 times 1/2 minus 1, and that's equal to 0. Interesting. So basically 0.5, so if we draw our master, we can draw our master. Why don't we do that? Why don't we draw our master element down here? This would be -1 to 1. This would be the master element. And so we have 0.5 here maps to, it's going to be basically 0. Oops. 0 in our master element. All right, so that's an example. Okay, so we see that that mapping function works out pretty nicely. And what we're going to do is use this system of coordinates, these intrinsic coordinates, in defining the shape functions. Okay, and these are going to be used to interpolate the displacement field. Why do we need to interpolate the displacement field? Well, in a given element, we know things like nodes, we know the positions, x, y, z coordinates of nodes, and we know the element connectivity. So basically what we use is all this information to describe what happens inside the element. We know exactly what the displacements are, or we have approximations through the solving process of the finite elements, what the displacements are at the nodes. We don't know those predictions for inside the element, okay, in this region. And so we need some tool, some approach to tell us, using these known displacements, what is the displacement value everywhere else. So that's why we use these. And we'll learn about this in the next video.